In this video, I want to talk about a specific type of population growth that can be modeled using what's known as a Leslie matrix. I'm going to start just with an example of this type of problem, and then I'll talk about more generally what sorts of problems can be modeled this way and how is this related to Markov chains and other things we've been doing. So this problem, I'm going to talk about squirrels in Boise. For those who have been in Boise, they know that it's the city of trees, and with trees come squirrels. There are a lot of squirrels. So let's suppose that we know that squirrels in Boise have the following rates of reproduction and survival. So what this chart is saying is that a squirrel who's age 0, so they haven't turned 1 yet, they won't reproduce, so there will be no new squirrels created by them, and 22% of them will survive to be age 1. For age 1 squirrels, the average reproduction rate is 1.6. So if you have 2 age 1 squirrels, you on average will have 3.2 new squirrels due to them. And their survival rate is 60%. So 60% of age 1 squirrels go on to survive to be age 2. And then finally, at age 2, we'll say that our squirrels have a reproduction rate of 2.1. So they more than double themselves, but none of them survive on to age 3. And we'll talk about kind of these details. You might say, wait, this isn't true. Like squirrels surely can live beyond age 3. And these numbers are not quite made up. I found them on the internet, but they're more chosen to make the problem work well, or they're not to be taken literally, right? And I'll talk about some of these assumptions that are going on here. So what I want to know is, let's say that in my neighborhood, we currently have 100 age 0 squirrels, 75 age 1 squirrels, and 90 age 2 squirrels. How many will there be next year? We certainly have enough information to answer this question, so let's figure it out. Alrighty, well, so how are we going to figure out how many age 0 squirrels there will be? Well, the age 0 squirrels are the new squirrels, right? And so they're created by reproduction. And so we have 75 age 1 squirrels, and they reproduce at a rate of 1.6. And then we also have 90 age 2 squirrels, which reproduce at a rate of 2.1. And so there will be 309 age 0 squirrels next year. How many age 1 squirrels will there be? Well, age 1 squirrels can only come from age 0 squirrels, right? 22% of age 0 squirrels survive. And so if there's 100 to start, we actually only end up with 22. So we have 22 age 1 squirrels. And finally, if we look at age 2 squirrels, well, these only come from age 1 squirrels. That's the only way to get an age 2 squirrel. You have to be 1 first. 60% of them survive, so 60% of 90 is 54. Right. Sorry, I'm concerned about right. It's not 60% of 90. It's 60% of 75, right? There were 75 age 1 squirrels. And so we had 75 age 1 squirrels. 60% of them survive. And so there were 45 age 2 squirrels next year. All right, so we figured out how many of each age there will be next year. Now, if you've watched the video on Markov chains, this should look pretty familiar. To be clear, this is not a Markov chain problem, and I'll talk more about that. But these sorts of calculations, hopefully in any situation, as you've worked through this linear algebra course, you start to get this feeling, wait, I could probably model this with a matrix. And there's lots of reasons that we'll want to model it with the matrix, one of which is that my next question is, how many will there be in 5 years? And I don't want to have to just do this calculation iteratively by hand. I want to be able to have a computer do it for me. And in order to do that, I want to be able to write down a matrix that represents this transition. So what's going on is that we're going to think of this as this calculation is we have some matrix times our starting population of squirrels is going to give us the next year's population of squirrels. And how did we calculate it? Well, if we look at our matrix A, our columns are going to represent where the squirrels are coming from, and our rows are going to represent where they're going. So what I mean by that is row 1 is representing the new age 0 squirrels. And so how do we get new age 0 squirrels? Well, we get new age 0 squirrels from reproduction. And the age 0 squirrels don't contribute new ones. The age 1 squirrels contribute 1.6 times their number. The age 2 squirrels contribute 2.1 times their number. And that goes in row 1. And if we look at this multiplication, we're going to multiply exactly what we want. 100 times 0, 75 times 1.6, 90 times 2.1. This will make sense. All right, the next row represents where the age 1 squirrels come from. The age 1 squirrels only come from age 0 squirrels, and they survive at a rate of 22%. Let's spread this matrix out a little bit. So they survive at a rate of 22%. And we don't get age 1 squirrels from anywhere else. And similarly, age 2 squirrels only come from age 1 squirrels, and they survive at a rate of 60%. So this is our matrix. And you can confirm that these calculations work. That is, if I plug in the matrix A, this is what we get. And the idea is that this first row is representing the fact that age 0 squirrels come from reproduction. This is the reproduction due to age 1 squirrels. This is the reproduction due to age 2 squirrels. Age 1 squirrels only come from age 0 squirrels, and age 2 squirrels only come from age 1 squirrels. This matrix is known as a Leslie matrix. We'll talk more about what that will look like in general. And this allows us to do calculations a lot more nicely because I don't have to write everything out each time. What I can say is if I want to know how many there will be in 5 years, I'm asking what's a to the 5th multiplied by my starting number of squirrels. And I did that with software ahead of time. And I got, now this answer is a decimal, right? So I'm rounding to 2 decimal places. That may seem weird since we're talking about squirrels. You know, there can't be fractional squirrels, but remember, this is a mathematical model. We would never expect a mathematical model to be exactly correct anyway. So this is saying that, look, initially I was getting worried, right? We started with, I don't know, around 250 squirrels, and then we ended up with almost 400 squirrels, and it looked like Squirrelmageddon, right? Things were getting out of control. But actually in 5 years, the number of squirrels has declined. All right, so the final question I have, which you might have thought of if you think about this in terms of the same sorts of questions we asked about Markov chains is, you know, what's going to happen in the long run to this squirrel population? Is it, and there's 2 kind of questions there. Is the population growing? Or is it declining? Right, initially it was growing. After 5 years, it looks like it was declining. What's it going to do in the long run? And also, is there some sort of proportion of each age? So that is to say, even if the population is growing or declining, so the numbers of each age are changing, maybe in the long run, 50% are age 0, 25% are age 1, 25% are age 2, even though it's growing or declining. And to look at the long-term behavior of the matrix, we look at its eigenvalues and eigenvectors. So this matrix A has only one positive eigenvalue. It has complex eigenvalues. In this case, it doesn't have negative eigenvalues, but that would be possible. But it has one positive eigenvalue, and that eigenvalue is, if I round, 0.82858. This eigenvalue has multiplicity 1, so there's a one-dimensional eigenspace. Software tells me that A has this eigenvector. Right, software usually only tells you one eigenvector, so I'll write it out as like this. And this, again, is the eigenvector corresponding to the eigenvalue of 0.82858. All right, so what does this mean? The eigenvalues and eigenvectors in Markov chains told us something about long-term behavior of the states of our situation that we were studying. What is this telling us? What this is telling us is that squirrel population declines in the long run by not 82.9%. I have to subtract that number from 1. Or let's phrase this differently. So that is, it declines by about 17% each year. In other words, it's being multiplied by 83% or 0.83, which is the same as declining by 70%. So the squirrel population is in fact declining. And it also tells us something about the long-term distribution of the different ages of squirrels. So if I take this vector and I normalize is the wrong word. Normalize means make a vector length 1. I don't want it to be length 1. I want the entries to add up to 1. But so if I multiply by a constant, or I divide by the sum of the entries, I get this vector. Where the entries do add up to 1. And this is saying that in the long run, (68.6%) of the squirrels are age 0, 18.2% are age 1, and 13.2% are age 2. So again, this single positive eigenvalue is telling us, because it's less than 1, that the squirrel population is declining. And in the long run, we're approaching this proportion of each age group, and each year, each of those age groups declines by 17%. But since they're all declining by the same percentage, they're still, as a proportion of the whole, they're still the same. All right, so I answered 3 questions related to the squirrel population. What's the population next year? What's the population in some number of years? And then we looked at the long-term behavior of the population. How much is it increasing or declining by every year in the long run? And we have this kind of stable percentages of the different age groups, even though the population itself is not stable, it's declining. Now I want to talk about kind of bigger picture. What are the important characteristics of this problem that allowed us to do these computations? And I'll eventually at the end, I'll dive into some of the details of the underlying math, but here I'm still just talking about what applications can we solve using this type of process. Okay, so what's important about this problem? Our population was divided into age groups of equal length. In this case, the length being 1 year. That's really common if we're talking about animal populations, things like that. But if we were talking about, for instance, human populations, and we didn't want to have to divide it into so many years, we could divide into age groups of length 5 or length 10 or something like that. Right? So what's important is that they're equal lengths so that we can think of things as individual time steps. And at each time step, we're multiplying by a matrix. What information did we need to know? We needed to know the rate of reproduction, that is, what for each individual in one age group, how many on average age 0 members are created by that individual. And we also needed to know the survival rate for each age group, what proportion of that age group go on at the next time step to be in the next age group. So that was all we needed to know. And hopefully you can convince yourself that this is a reasonable model in a lot of situations. Most examples I've seen are examples from, I guess, ecology, where we're modeling populations of animals. And there's certainly some assumptions here, right? We don't have outside squirrels joining the population. But generally speaking, as long as you don't have outside animals joining a population, hopefully you could get some sort of measurement of survival rate and reproductive rate, and you could get a sense for whether a population was increasing or decreasing or staying the same in the long run, and how that population was distributed. The only assumption that I think that I mentioned that might seem unreasonable is this everyone dying off at a certain age thing. Right here I said, hey, and all the squirrels die off after age 2. It turns out that you don't actually need that assumption for a lot of population modeling, because if your concern is the long-term survival of the animals, all that you need to do is consider them up to the point where they no longer reproduce. So that is to say, let's say squirrels can't reproduce after age 2, but they can survive till age 8 or something like that. In terms of thinking about the long-term survival of the population, we don't need to keep track of those squirrels. So in other words, at some point, either reproduction rate hits 0 or survival rate hits 0, and at that point, we can kind of cut off our calculation. We don't need to keep track of the rest of those squirrels because they aren't contributing to the creation of new squirrels. And in most, I think, modeling of animals, that's going to allow you to not have some crazy huge matrix. Speaking of the matrix, what does this matrix look like? What's important about this Leslie matrix? What characteristics does it have? So first of all, each row is corresponding to how we get new members in the next year of that age group. And this means that row 1 is all of the reproductive rates. And reproductive rates, the only thing that matters is that they're all non-negative. We can't have negative reproductive rates. They're either 0 or they're positive, but they could be large numbers, right? If we're talking about like rats or something like that, maybe you would have reproductive rates of like 20, something crazy. Below that, we're talking about survival to the next age group. And so most of these entries are going to be 0. Because you can't skip, or sorry, you can't, if you're going to end up in age 1, you can't get there from age 1 or age 2. Right? If you're going to end up in age group 2, you can't get there from age 0 or age 2. In each of the remaining rows, there's only one entry that can be non-zero, and it's the one just below the diagonal. Right? So this is the diagonal, and just below the diagonal is representing moving up in age group. Those numbers, they could be 0, right? Everyone can die at some age. It's possible that no one survives, but they can't be bigger than 1. And they can't be negative, right? They're survival rates. So we have a lot of zeros, and then just below the diagonal, we have numbers that are between 0 and 1. So that's what our Leslie matrix will look like. And what properties does this matrix have? This is kind of starting to get into why this whole process will work. as long as there are two consecutive age groups with positive reproduction rates, so as long as two consecutive age groups have positive reproduction rates, so you need to have some age group with a positive reproduction rate. If no one's reproducing, there's no point in studying these animals. They're just going to die off. But here we have two consecutive age groups that are actually reproducing. And as long as that's the case, this matrix is going to have some nice properties. It's going to have exactly one positive eigenvalue. And this eigenvalue represents a steady state solution in that the eigenvector, or it's a one-dimensional eigenspace. So if we choose the eigenvector with entries adding up to 1, will give us the long-term distribution of the age groups. And that was what we saw in our squirrel example. I didn't show you the calculation, but if you calculated the eigenvalues and eigenvectors, you would have found just one positive eigenvalue. In this case, the other two were complex eigenvalues. And that's a one-dimensional eigenspace. This eigenvector tells us nothing, but once we divided by the sum of the constants to get a vector whose constants whose entries added to 1, we got the long-term distributions of the different ages of the squirrels. So I'm done with the main part of the video, kind of how to do these sorts of problems. Or actually, sorry, that's not true. I was going to say I was done. There's one more thing I want to address, but I'm going to address why at the end, why it is that this matters, like why we need two consecutive age groups to have positive reproduction rates for this to work. But before I say that, it's important to distinguish this type of problem from Markov chain problems. So how are these things different? So there's a few ways to look at this. In a Markov chain problem, the population is fixed. That is, I gave this example where, people in a town are switching between cable providers, but no one's coming in and out of the town, and no one's allowed to not sign up for cable. And so you have a fixed population. Here, the population is not fixed. The population is, you're reproducing, you're producing new members of the population, and the population can also decline, right? Members of the population are not surviving. So in these Leslie matrix problems, we have a non-fixed population. The other thing about this problem that's a bit different is that even though we have a non-fixed population, the way in which individuals move from state to state is very much restricted. Individuals can only move to the next age class. They either don't survive or they move up to the next age class, and then we can also create new individuals in the age 0 class. In a Markov chain problem, generally speaking, individuals can move from one state to any other state. And then finally, in terms of matrices, this Leslie matrix, in the Markov chain problems, all the columns had to add up to 1 because the population was fixed. Everyone had to start in one state and go to another. That's not the case here, right? In this Leslie matrix, the columns do not add up to 1. I mean, none of them do. It's possible that they would, but there's no reason that they should have to add up to 1. Okay, so that's how we have kind of differences from Markov chain problems. They're very much similar. They employ similar ideas. A lot of the computations are similar. A lot of the interpretations are similar, but we are in a fundamentally different situation. I want to talk about this why two consecutive age class thing. And I'm not going to, and I should mention, this is kind of the why this works part of the video. If you're not interested in why, you could just stop the video. But if you're wondering, why would that matter? I'm not going to explain why that guarantees you a single positive eigenvalue. That's a bit beyond the scope of this video. It's not crazy to show, but it requires a lot more mathematical analysis. I want to show you what goes wrong if you only have one age group that's reproducing. And it's relatively easy to see with a simple example of a Leslie matrix, about the simplest one we could write down, what's going wrong. So let's say we get a Leslie matrix that's this. So this certainly satisfies the properties of a Leslie matrix, right? In our top row, we have everything's non-negative, and in our bottom row, the only non-zero entry is the one below the diagonal, and it's between 0 and 1. And so what is this saying in terms of the population? If we think of this as just age 0 and age 1, what we're saying is that individuals at age 0 don't reproduce, but all of them survive to age 1 and then reproduce at exactly a rate of 1, and then they die. They're gone, or they can't reproduce anymore. And so what ends up happening here is pretty easy to see if you start to take powers of this matrix. When you square it, you get the identity. When you cube it, you get A back. And what you can see is that as we take powers of this matrix, we're just going to go back and forth between the identity and the matrix A. Or in other words, if we start with the vector, let's say 100, 0. So we start with 100 age 0 and 0 age 1. Then at year 1, there's no reproduction because none of the age 0 individuals reproduce, but they all survive to age 2. And then at the next step, all of these age 1 individuals reproduce and create age 0 individuals, but none of them survive, and there were no age 0 individuals to move along. And what you see is that we're just going to cycle back and forth between there being 100 age 1 and 100 age 0. And we're not going to have some sort of long-term steady behavior. Now, this matrix has it's a very simple matrix to analyze. Its characteristic polynomial is x squared minus 1. It has eigenvalues of plus and minus 1. And it's real easy to see that, for instance, if we want to choose something like this, 50, 50 is an eigenvector. With eigenvalue 1. So if you start with equal numbers of age 0 and age 1, you'll just always have 50 of each, or whatever number you started with. But if you start with different numbers of age 0 and age 1, they're just going to oscillate back and forth. And so depending on your starting state, you can have different long-term behaviors. You can have this sort of oscillating behavior, or you can have, if you actually have just an equal number to start, you can have this actual steady state behavior. And this is an example showing that things can go wrong when you don't have 2 consecutive ages with positive reproduction rates. And the general idea is that the issue is caused by the lack of reproduction in one of these age groups. And as soon as you have 2 consecutive age groups, you start to, I guess in some sense, lose memory of the initial condition, right? Because we only have one age group reproducing, we can end up with these cycling behaviors where the initial condition actually matters. Whereas as soon as you have 2 consecutive age groups who reproduce, whatever the initial condition was is going to get blurred out by that fact. Again, I'm not going to go into the details of exactly why that works. So in any case, this is nice because this assumption that there are 2 consecutive ages with positive reproduction rates is almost always going to be true in application, right? If you're studying the reproduction of some sort of species and you don't have consecutive ages with positive reproduction rates, you should probably change your age gap, right? If you're studying an animal whose lifespan and reproductive span is so short that they only, let's say, reproduce in a certain year of their life, maybe you should split that into months or 4-month spans of their life. So it's not even that unreasonable of an assumption. All right, so hopefully that video was helpful and gives you a sense for how to solve these sorts of population growth problems that can be modeled with the Leslie matrix.